Um, Last week, one of the main things we took a look at was just kind of the physical ways earthquakes happen. So, um, looking at the faults and the normal faults and the reverse faults and things like that. And then also talking about the P waves and the S waves, the surface waves, the body waves, how those move through. We talked about how many, uh, um, sorry, I'm having brain farts this morning, how many seismic stations there. That's what I'm trying to get at. How many seismic stations we need to locate where the epicenter or the hypocenter, the focus of those earthquakes are. So remember, we needed 3 of those to figure out where the earthquakes were. So that's what we're going to build on that today, and we're going to take a look at how do we determine the magnitude, and now how do we determine the intensity of these different earthquakes? Because what we're going to see is that you can have a relatively large magnitude earthquake and it doesn't do much damage at all. The intensity is not super high or super great. And sometimes you can have a relatively low magnitude earthquake that if it just hits in the wrong area or the wrong types of buildings, it can cause catastrophic damage. And so that's what we are going to be taking a look at. All right. So also, I just want to say, the mad props part is most everybody has all of their sketch notes in. A lot of folks are pretty up to date. If you're not up to date with the sketch notes, do what you can to get them in. I think tomorrow I'll be sending out, there's a few emails I'll probably be sending out to various people in different classes. There's like a couple in each class that I haven't got a link for that's working, or just checking in, making sure everything's okay. All right. So that's what we'll be doing, but everybody else, you guys are hanging in there, doing great. So, give yourselves a pat on the back. We're halfway through. We'll look at quick geo news, talk about measuring quakes and magnitude and intensity, earthquake hazards, earthquake risk assessments, and then we'll go from there. I forgot to give you guys sunshines and blues last week, so that's blank. And then geo news for you to geo knows. Well, yesterday, holy moly, that was a crazy strong wind event. And basically it happened through what we call an inside slider, which is a low pressure system that comes in from, somebody's coming in there, that comes in from Canada and drops its way down. And what you're seeing on this map right here, this is what it looked like yesterday, right around this time yesterday. The jet stream was flowing right over the top of Northern California. So this is up at about 20,000 feet, somewhere in that neighborhood, 15, 20,000 feet where airplanes fly. And you can see in different areas here, we're talking like 129-mile-an-hour winds way up high. And some of those winds eventually mix down lower and make the strong winds we had yesterday. And since our valley pretty much aligns with the same direction that the wind was coming, it just funneled everything and made it really strong. So I hope you all survived. One of my classes yesterday, my neighbor's tree blew down, and that was really fun. Or at least 3 huge branches of like a 150-foot tall pine tree blew down and smushed part of a car. So that was a really interesting thing. Winds events this time of year kind of stink because all the trees have their leaves on them still, and that adds more friction, right? That the wind can catch on and blow things over. And so I did put a link right down in here if you guys want to take a look at this one on your own. It's an interactive link that you can go to and see like the peak wind gusts. So in Turlock, this was as of yesterday afternoon, but I think the peak gust I saw down in Turlock was about 39 miles an hour. Modesto Airport, I think, had 41 miles an hour. Let me see. Somebody says garbage day from yesterday. There's garbage flying. Oh my gosh. Yeah, I can imagine all the garbage just flying, especially if folks don't have like the lids and stuff tied down or things like that. Yeah. So pretty crazy. And, the dust advisories, the wind advisories with the dust that got kicked up, the particulate matter, it's not quite as bad today for sure. But it was still bad air quality, but not from smoke. It was just from all the dust that was up there. So I hope nobody had to wash their cars beforehand because I think we're going to need it a little bit more. So I won't leave you with everything being kind of bad and crazy, but there's We're going to be learning about weather models too in about 4 or 5 weeks time or so. And what those kind of do is they're able to piece together what the atmosphere is doing now and then make predictions about the future based on how past events have gone, right? And so we take these models, and what's kind of cool here is some of them are getting enough to where 10 days out or so, they're getting enough to become reliable and say, oh, here's something we should be on the lookout for. We don't know the exact timing of like when rain and stuff will be coming 10 days out, but there's a possibility. And right now it seems like it's a higher than average possibility for Northern California, and we'll call moderate possibility risk of heavy precipitation in between that week of somewhere between the 20th and the 22nd. So usually what this means is maybe an atmospheric river or a strong storms coming in from Alaska. But the reason they're putting this out there now is there's so many burn scars everywhere in California that, oh my gosh, if you add flooding rains to that, where there's not as much wood catching the water or slowing the water down before it runs off the hills, it could be not so good in some areas. Luckily, all of our dams are really low right now, so it should be able to catch a lot, but it just might be catching a lot of wood and debris and muddy water and stuff. But so we could see some wetter weather coming up in the next few days, or not few days, but next week or so. So just remember that. Remember it next week. Maybe next week at this time we'll be saying, oh, hey, watch out, it's going to be really, really rainy. So we'll see how that goes. But as a general rule of thumb, unless it comes from the National Weather Service, don't believe any of the 10-day forecasts or anything like that. A lot of those websites are total bunk. And really, we can only get pretty high precision accuracy within 4 or 5 days out of what's going to happen here. So did somebody have a question? I thought I heard somebody, but maybe not. I don't know. Okay. So here's what we're looking at today. Then we're going to be looking at measuring those earthquakes, the difference between magnitude and intensity. So add a few sketches here. I've noticed on some of the sketch notes, I don't like explicitly say sketch, like some folks leave the sketch parts out. So just add a few little diagrams that go along with this to help explain what in the heck you're talking about. Okay. We'll talk about seismic waves and amplitude and how that changes over different areas. So we'll take a look at how these soils affect that, and we'll go from there. All righty. Probably the end of this week is when we're going to get into the major parts of all the earthquake hazards. And then your extension question here, which I don't know why it got covered up, but I'll fix that. It says, imagine you had the good fortune of being able to purchase a house from which to remotely work or to remotely go to school, right? You just had all the money in the world, but you had to choose for some reason, even though you have all the money in the world. You had to choose between Turlock, Santa Clara, or a beach in Eureka in Northern California, or in the Sierras near Lake Tahoe. If you had to choose one of those houses, what questions would you ask your realtor? So you're like, okay, I'm going to buy a house in Tahoe, or I'm going to buy a house in Santa Clara. What questions would you ask your realtor regarding earthquake hazards in each of those cities before making your final choice? And like, how do you know that the house you're buying is earthquake safe and things like that? Or maybe it's not. So maybe you need to invest a little bit to upgrade that. So this is a real cool question because it's a very true to life thing that you may get to experience. Hopefully houses will become affordable for everyone again sometime. But if you need to buy a house, or even if you're renting a house, these could be some good things to know to figure out if you're going to be safe or not during an earthquake. So with that being said, let's get into it. We got a couple of Jamboards and fun interactive things I think to do over the next couple of days here. But when was it? Last Thursday, we ended up talking about, trying to figure out the P's and the S waves and triangulating where the earthquakes were. But I didn't show you how we calculate the magnitude of an earthquake. So once we know the P waves and we know where the S waves are and the surface waves, we can measure the amplitude of those S waves and the surface waves. And those amplitudes give us a little bit, the first hint of how big an earthquake was. The more energy is released, the bigger the jiggles are going to be on the seismograph here on the seismometer. All right, that's one thing. However, that's kind of the old school, the Richter scale. You may have heard about the Richter scale. That's one way of doing it. We now have a much more advanced way of doing it that luckily we've matched all of these seismographs up with actual field work where geologists have dug into the hills and have like ripped apart, dug in trenches basically and ripped apart faults. And we're able to measure specifically how much fault broke during an earthquake, and they can directly tie that to what the seismographs say. And so now within like 2 or 3 seconds of an earthquake, the seismographs can predict how much land has been moved and how big the earthquake was. And we call that the magnitude. So the magnitude is the measure of the size of the seismic waves and how much the fault surface has broken and moved. So to give you kind of a primer for this, this was a magnitude, oh man, I forget now. It was in April 15. I think it was about a magnitude 7 in Kathmandu, Nepal, which is a pretty amazing place in the Himalayas. But I just want to show you what it's like to experience. Oops, let me see, let me shut this. I don't want to share that sound. It's kind of annoying. Magnitude 7.8, that's what it was, I forgot. But it struck in the middle of central Nepal. And so this video shows all of that motion of the GPS. So what you're going to see here is just people walking around before the P and the S waves hit. And then you're going to see up in the right-hand corner of this video, the GPS that kind of moves around as the earthquake goes through there. So you can see how the waves affect it. So up and down, left and right and stuff like this. But you can also watch and see how it affects the people. And I would also keep an eye on this corner of the building right here and what people are doing and their reactions. All right, so it's like closed circuit TV. Here's the GPS. So not much happening. Ooh, there's our P wave. You can see there's a little bit of displacement on the GPS unit. And then boom, here comes the S waves. And then here come the surface waves. And when we say it's hard to walk during a big earthquake, my goodness, this is what we mean. All right, it's like walking. It's like being on a cruise ship in the middle of an ocean that's just, you know, crazy rocking and rolling. And I don't know if you guys saw this, but right, people are trying to move away from these buildings. Remember, we saw brick buildings were bad last week. Ooh, that lady's lucky. Watch, she gets tossed this way. This lady's like, oh no, ooh. Had she been a few seconds earlier, you'd had some of that brick would have just come right down on them. I mean, so that person is super lucky that she didn't get injured in there. So this is kind of the things that we're going to be seeing. And you can see how those surface waves are now causing the GPS station that was there to kind of roll back and forth and finally get smaller and smaller and smaller as the waves kind of peter out. But you can still see, I mean, it's still going through there. So this is what it's like when we're talking about the magnitudes of earthquakes. We're measuring the amount of seismic waves measured on these different magnitude scales. So how do we measure that? Well, I'm going to show you this. This is the guy like Toby from The Office here. We used to measure the Richter scale, but it wasn't super accurate. So here's kind of a way of them explaining how we can now measure the offset of the fault. So how much of the fault breaks and moves and how much shaking that causes. So that's what this is going to explain. Oops, maybe.
That the signals
there we go. Oops, let me share my sound. Sorry, I forgot to do that. There we go. Okay.
Adequately represented, like not being able to hear the bass notes on your laptop speaker.
So the old Richter scale, what they were saying and what we're ending on here, picking up from is it just wasn't sensitive to really big earthquakes. And so they had to come up with a different way to measure.
That meant that the Richter scale underestimated the size of large earthquakes. Seismologists have since developed far more sensitive seismometers that, with faster computers, have enabled them to record and interpret a broader spectrum of seismic signals. These improvements allowed them to better determine the energy released by large earthquakes. In 1979, they connected the seismograph recordings with the actual physical displacements that occurred during an earthquake. The result was the moment magnitude scale. Seismologists no longer look at only the amplitude of seismic waves, but instead use much more information contained in the seismogram to calculate what is called the seismic moment. The seismic moment, which defines how much force is needed to generate the recorded waves, is defined by this equation. mu times distance times
Well, I just want to say, don't stress out about this equation. You don't have to memorize it or anything, but I do want to show you how it's calculated. So how do they figure out how big it is? Well, this is a constant. So the D and the A are the things to kind of pay attention to here, just the concept.
area. Mu is rock rigidity. It describes the resistance of the rock to bending when force is applied and is a constant for a given rock material. More elastic energy is stored bending rocks of high rigidity than is stored bending rocks of low rigidity. For example, this brick has high rigidity and when bent or sheared would yield a strong earthquake.
That means it takes more energy to break it, right? If you have a brick, you have to push a lot of energy on it or put a lot of energy into it before it finally breaks and moves. And so that high rigidity actually stores way more potential energy that's like trying to break it. And so when it does break, it goes. Versus if I just had a spaghetti noodle, you have to hardly put any pressure on that or any stress on that before it broke, right? It's not going to hold nearly as much energy as a brick.
The cake has lower mu and shears easily. Rock rigidity is lower in the crust than it is in the mantle. As mentioned earlier, in most cases, distance and area can be determined by mathematical modeling of seismograms. D is the distance that the rock slipped along one side of the fault zone relative to the other side. In the 1906 San Francisco earthquake, this fence line was offset over 3 meters. A is the estimated area of the fault zone along which the rock slipped.
So this is the big part here. When we talk about those normal faults, the reverse faults, even the strike slip faults, when we talk about an earthquake rupturing, this is what we mean. How much surface area actually broke. So in this earthquake that moved everything 3 feet, all of this busted open, right? The Japan earthquake, the magnitude 9, whatever earthquake in Japan, 2011, that thing, I think there were some place, I think it was like over a 300-mile or 300-kilometer long rupture. That's how much broke in one earthquake. So that just kind of puts things in perspective. And now we can use those seismographs to calculate and figure out and model how much stuff is broken right away.
D. It defines the area that actually ruptured during the earthquake. Let's watch an earthquake happen. The arrows show forces building on opposing sides of a fault. Growing stress that will be relieved in the earthquake will be shown in red. Here we see blocks of rock move in opposite directions along a strike slip fault zone, such as the San Andreas Fault in California. Potential energy, in the form of elastic energy, is stored in Earth's crust or mantle, building stress as the ground slowly deforms between large earthquakes. Take a look below the ground at the earthquake rupture that defines the seismic moment. That equation is then plugged into the moment magnitude equation, which is used by seismologists to measure the size of earthquakes in terms of the energy released, not just the amplitude of the recorded waves. The constants in the moment magnitude scale are chosen such that at smaller magnitudes, the moment magnitude matches the Richter scale. To truly appreciate this, consider the changes in the earthquake rupture required to increase the moment magnitude by 1 unit. Either the area of rupture or the slip distance or both must increase so that the
that's a great thing to think about. You could have a narrower area, but then have a greater distance of slip could cause the same amount of moment magnitude. You could have maybe a huge area rupture, but not very much distance, but because so much broke at once, that's going to cause a lot of energy to be released. And there's a really great analogy here that I want to show you that uses a spaghetti noodle as a
product of slip distance times
model.
Area increases by a factor of 32.
So check this out.
While the amplitude of shaking causes a factor of 32.
Here, this is important right down here. So when you move up from one magnitude to the next, from like a magnitude 5 to magnitude 6, the amount of energy here increases by a factor of 32. So it takes 32 times more energy to break the rocks of a magnitude 6 than, or 32 times more energy is released, I should say, when a magnitude 6 breaks compared to a magnitude 5, which is just crazy to think about. And we'll see the ramifications of that right now.
While the amplitude of shaking caused by a magnitude 5 earthquake is 10 times larger than for a magnitude 4 earthquake.
So I just want to mention to this too. So the energy is, like we said, is 32 times greater. The amplitude on the seismographs only go up 10 times for each magnitude of an earthquake. So if you're looking at the squiggles on a seismograph here, a magnitude 5 would have 10 times taller peak or 10 times taller amplitude than a magnitude 4. But the amount of energy released would be 32 times as great, okay?
The energy released increases by about 32 times for each unit increase in magnitude. To understand the scaling, we'll look
Here's
at
our
the effects
spaghetti
of the
model.
rupture
This is
area
great.
by using pasta as a model for magnitude. The cross-sectional area of a strand of spaghetti is about 1 square millimeter. When you break the noodle, it makes an earthquake of, let's just say, magnitude 5 for our model. Mu is constant for all strands of pasta, and for D, we'll use 1 millimeter of displacement across the fault. So here we see the pasta break and move laterally 1 millimeter. To increase it to a moment magnitude of 6, we multiply it times 32. The surface area is 32 times higher, yet the amplitude is just 10 times higher. To reach a magnitude 7, you have to multiply 32 times 32, and you get roughly 1,000 strands, or about a pound of spaghetti noodles. To get a magnitude 8, you need 32,000 pieces of spaghetti.
That's a lot of
A
spaghetti.
magnitude 9, on the other hand, would require 1,000,000 pieces of spaghetti.
So notice every time we're moving down, we're multiplying each thing by 32, right? Compared to the original magnitude 5. So 6 is 32 times greater than that. A 7 is 1,000 times greater than a 5. An 8, if you do 32 times 32 times 32, gives you about 32,000 times greater. And then a 9 is 1,000,000 times greater than a magnitude 5. So really what that means is you would have to have 1 million magnitude 5 earthquakes to release the same amount of energy as 1 magnitude 9 earthquake. And so when you think about that in the Earth's history and stuff, 1 magnitude 9 is basically more earthquake energy released at once than, usually 5, 6, 7, 8 years worth of time on all of the earthquakes on the Earth combined. That's how massive and major they are.
Magnitude 9 releases 1,000 times more energy than a magnitude 7 earthquake.
So we had like a magnitude 6.9 in Loma Prieta, which is right around a magnitude 7 back in '89. And then the Japan 2011 earthquake was literally about, if you go from here to there, it's 1,000 times greater. So it's about 1,000 times greater than the magnitude 6.9 we experienced, or if you were alive, experienced back in 1989. If you weren't alive, it was a pretty impressive, intense thing. And if you do have family or relatives or know of anybody that lived in the area during 1989, you should ask them about it. So how do we measure those magnitudes? Well, like we just kind of saw in that video, it measures the amplitude of the largest seismic wave. And then it can also use mathematical modeling then to figure out how much offset of the fault there was. So here's a 1906 picture from San Francisco that shows one of their water lines that busted, which was one of the main reasons the city burned down, right? So a couple of things just to reiterate here is that the magnitude scale here is from 1 to 10. So it goes from 1 being the smallest, and you can actually have, believe it or not, the way things work, you can have a negative magnitude every once in a while, but those are super small. So it starts from like a 1 all the way up to a 10. There's never been a 10 in Earth's history. Pretty much theoretically impossible, we think. So, high magnitude 9s might be like kind of the theoretical limit based on how much rock's stress can hold before they break. And the big thing here, just like they said in the video, if you go up 1 unit of magnitude, so if you go from like a 1 to a 2, that's 10 times the amount of seismic wave energy, but it's 32 times an increase in energy level. All right. So instead of, calculating all that stuff and trying to figure out how it is, the USGS has a really cool, I'll put it in the chat here, has a really cool link called How Much Bigger Calculator. Now, maybe they could have used a catchier name. I don't really know. But basically, the way this calculator works here is, and you'll be going to this in your small groups with breakouts here in just a minute. The way this works is you just type in 2 different earthquake magnitudes. So, and you're going to pick some real ones here in a minute. So let's say there was one magnitude 8.7 and the other one was a magnitude 5.8. You say, oh, how much bigger was this one than that? You hit calculate and it does the math for you, right? So instead of having us to go do all that stuff, it's a pretty slick little device to have. So it's a difference in magnitude of 2.9. So a magnitude 8.7 is 794 times bigger than a magnitude 5.8 in terms of shaking, right? In terms of the amplitude. But in terms of the energy released or how much stronger it is, look at that. It's 22,000 times stronger. So it would take the energy of 22,000 magnitude 5.8s to equal the energy of 1 magnitude 8.7. So when we're talking about these logarithmic scales and just how massive these things are, that's what we're talking about here. All right. So let me get open this other little Jamboard here. Comparing the magnitudes, copy link, put that in here, make sure it's the right one. Yeah, okay. Tuesday, Thursday. So you guys should have this Jamboard link, and let me make sure you guys can all edit it. Yep, everybody can edit it. So I'm going to put you in your groups, and basically all you're going to do is you're going to go to this website, which is the Earthquake Viewer. Boom, boom. This is the official USGS Earthquake Viewer right here. These are pretty much all of the live earthquakes that have happened in anywhere, well, if they're big enough, anywhere in the world that you can zoom in and zoom out of. It's very similar to the other Earthquake Explorer that we looked at, except this one doesn't do all of the like cross sections and things like that. But what it does do is you can zoom in and you can look at different places. You can click on that, and oops, when you click on any one of these or off to the side, you'll notice it says, oh, magnitude 1.4. And if you want the official USGS stuff on it, you can click on it and it'll tell you all the important official information that you need. And then you can just close this tab. One of the things that just happened this morning, there was a magnitude 6.4 over in Greece, which is pretty decent in size, right? Oh, you know what? I want to see what earthquakes do I have on here? Oops, sorry. Settings. 30 days, all magnitudes. So I have 30 days, all magnitudes US. What you might want to do is just go down to like 7 days. Let's see. That's all worldwide. Let's see here. Yeah, I guess 30 days significant, 30 days. You could do 30 days magnitude 2.5, and that's US and world, I think, or just leave it on like that, whatever. But it'll show you all these different earthquakes from across the world. So there's a magnitude 6.4 over there. There was down in the South Pacific earlier this week, like down in Vanuatu. There was a magnitude 7-ish somewhere in that neighborhood. This one's a magnitude, there it is, magnitude 7.3 that happened out there. So these are some of the things that you can take a look at. But what you're going to do is just click on that link within your small group, choose 3 different earthquakes, and then go to the earthquake calculator, type in each of those magnitudes, and tell me on your Jamboard here, where's the quake location? So what's its latitude, longitude, and depth? And you don't have to type all of that. If you just click on these, like if you click on that, where'd it go? There we go. If you click on it, and then you can just highlight all of this stuff right here in the bottom left, just copy this. And then if you go back into your Jamboard like this, you can, on your sticky note, hit paste. Oh, look at that. And it just pastes everything right there. All right. So you can put that in there and you can give it a name if you want. Like some people aren't good with latitude and longitude, so you can give it a name. But we're just looking for 3 different quakes. So you choose 3 different quakes, and then you're going to compare the difference between 1 and 2 and 2 and 3. And if you want, you can compare the difference between 3 and 1 as well. All righty. So this should take only about 7 or 8 minutes. It's not like a super duper long one, but it's going to give you some time to explore those maps and do some comparisons. How much bigger are these earthquakes from one another, which is kind of cool. All right. So I'm going to put you in quick little breakout rooms. yeah, like probably 7 minutes or so, and find those 3 different quakes, put those down there, and then compare those magnitudes, and you can kind of just like fill in the blanks of those other blue ones that are down there, the blue sticky notes. Alrighty, so we'll do, hey, look at this. We can do 7 rooms. And so we'll do 7 rooms of 3 and say hi to everybody. Make sure you're doing your best to participate and talk about it. You guys can share screen, whatever you need to do. Maybe each person choose one earthquake. It's up to you guys, something like that. Alrighty, so we'll go for, let's say 8 minutes here. And that should be plenty of time to get some ideas down on paper. And here we go. Jaslyn, are you seeing the breakout room? go. Got to make sure I'm not on mute. So good job. All right. It looked like everybody was having an interesting time choosing the different earthquakes and then finally punching into the calculator there to come up with that. So really good job. And, personally for me, this earthquake calculator is really helpful when communicating if we have earthquakes nearby, on Twitter or social media or something like that. When people start getting a little worried, oh my gosh, it's a magnitude 4 or something like that. Well, here's some perspective, right? Or if somebody thinks that's really bad, like, well, we have potentials for magnitude 7, 7.5s along the San Andreas, potentially magnitude 8s in some areas along the San Andreas. So, it helps to give people an idea of just how much stronger a magnitude 8 is compared to a magnitude 7, so that, we can plan and prepare, especially politicians. And politicians are elected by us. So we need folks to be able to communicate with them how we need to stay safe and what we need to do to prepare, because it's going to be way more cost effective, right, to invest a little upfront than it is to have to rebuild everything if it's completely destroyed and damaged, not to mention loss of life and things like that. So I always enjoy also seeing which earthquakes people choose, like where they go and what they look at. So good job on that. And now I got to find my slides. Here we go. All righty. Oops, I don't know what the heck that one's open for. Oh, that was yesterday's. That's why it's open. All right, so that was the magnitude. Now we're going to get into the difference here of what we call the intensity. So the magnitudes never change for an earthquake. All right, that's the one thing I want to, well, for an individual earthquake, it doesn't matter where you measure that earthquake from in the world, the magnitude is always going to stay the same. So a magnitude 7.1, if it ruptures in Santa Cruz, we feel a magnitude, the effects of the 7.1 in Turlock. All right, it always stays a 7.1. That's a physical measurement of the fault breaking, how much shaking it's done as well. All right, or the amplitude, I should say, of what's being recorded on the seismographs. So that's a little bit different than intensity. So intensity is the measure of the amount of shaking, but not only shaking, but shaking and damage that an earthquake creates. And so really the big thing here is that it's based on the damage. And back in the 1800s in Italy, a person named Mercalli was the first one to kind of start quantifying earthquakes based on how bad the damage was. And that was kind of the first ways they started measuring earthquakes, because they didn't have seismographs to measure it. So they went around and looking at damage. But what they started realizing, and what we now know, is that sometimes you can have really damaging earthquakes, that are small. You can have really big earthquakes that aren't very damaging. You can have earthquakes that are fairly big, don't do much damage to the buildings nearby, but maybe 50 miles away, those same earthquake waves have hit a different type of soil or bedrock, and the destruction is completely different. And so we have a scale for that, and that's what we call the intensity. And this is kind of like what you would feel at an earthquake, like how much shaking would you feel at that earthquake based on this. So this was an earthquake in 2008 in China. It was, I think, a magnitude 5.8 or something like that, but it hit some older construction that wasn't built for earthquakes at the time, and caused like schools and apartment buildings and all sorts of things to collapse, which was pretty tragic. So knowing how things move and shake in the ground can help us build things that don't get messed up. And so, and I'm not trying to be glib here, but the way to remember intensity is if you have a very intense earthquake happen in a very populated area, what can happen is you end up living in the tent cities afterwards, because if you have, this was in Chile in 2010, they have very good engineering standards, but the magnitude, I think it was like an 8.5 or 8.6. It was such a huge earthquake that it even caused a well-engineered building to topple. I think it had some soil foundation issues. But after that, right, you can't live in there, and then nobody wants to live in buildings during all the aftershocks that are happening that could maybe cause other damage. So they set up tent cities and things like that in countries that have the resources to do that, or if countries don't have those resources, that's when the United Nations hopefully will step in, and humanitarian aids will step in to provide safety and shelter, temporary shelter, as the earthquake sequence and aftershocks kind of die down. So intensities can be really strong. And here's what's different about that in terms of how you know that the difference between magnitude versus intensity. The intensity, we use Roman numerals here. All right. So if you don't remember Roman numerals, each one of these is a 1, the V is a 5, put a 1 in the front, that's subtracted. So that's a 4. And then if you have an X, that's a 10. And so an I in front of an X, a 1 in front of the X means 9, because it's like subtracting 1. So it goes anywhere from like a 1 to a 10. Sometimes we can get 11 or 12s in intensities here. A good example of that is Port-au-Prince in Haiti, the Haiti earthquake, which was July 2010. Or I mean, January 2010, 11 years ago. And they had another pretty significant one right over here just a few months ago that is still causing a huge amount of damage. But we'll talk about this a little bit more, why they had so much damage compared to other places in just a second here. So like I said, these Mercalli scales, they measure the intensity of the earthquake based on observable effects and damages at different locations. And so if you want to kind of put these into words, the modified Mercalli scale, this is kind of the accepted verbiage basically around the world that most different agencies, government agencies around the world kind of use now. For us in Turlock during the 1989 earthquake, we felt basically strong. So we were probably like a 5 or a 6, somewhere in that neighborhood in Turlock. There were some parts of the Bay Area though during that earthquake that had almost a 9. And that's because there was complete damage to some of these well-designed buildings that collapsed and fell down. So these are some of the words here as they go through, and you'll notice damage is negligible in buildings of good design, slight to moderate and well-built structures, but considerable damage in poorly built or badly designed structures. So we're going to see what constitutes good design, what constitutes bad design, and what keeps you safe. So if I were to put some numbers, give you some pictures to see what the results would be of like a intensity of 4 or a 5 here. This was an earthquake in Nevada, I think about 10 years ago, that just knocked everything off the shelves, right? And so the earthquake itself wasn't super huge. It was good enough, but it caused some damage, knocking all that stuff off the shelves. And there were a few other houses that had some damage in this area. In the town of Wells, that this is the same earthquake, except this is now, instead of in a well-developed grocery market, we're in kind of an older historical town, kind of a ghost town out in the middle of Nevada. Brick buildings, you notice, these were all 2- and 3-story buildings here. And that earthquake caused all those buildings to collapse. So again, brick, brick, brick falling down and not being so great here. And what's really sad about this picture is when I took these pictures, we showed up a year after the earthquake. We happened to be driving through a year afterwards, like, oh, I wonder if we can see anything. And we were just shocked that everything was still piled up on the streets. It's just kind of a small community, only a few hundred folks, and they hadn't had the state resources or community resources to even clean up anything yet, which is just kind of mind-boggling. So when we talk about equity, this is one of where it rears its head too. So when we're talking about also the intensity, probably the most intense one in our lifetime in terms of complete and utter devastation to community and places was Haiti. And so Haiti had a maximum intensity of about a 10 or 11 on the Mercalli scale here, Roman numeral. And you can just see just row after row of concrete buildings collapse, collapse, collapse. So a lot of folks died in collapsed buildings, but it's a tropical environment. It's warm. And so after a few days, supplies started running out. The airport was damaged. The ports were damaged. It was hard to get aid in there. And then once they finally did started getting aid in there, it's a very dense population. There's lots of folks there that live in this area, things like 1.2 million people, and basically something a little bit bigger than the size of Turlock and Modesto. And so it's hugely densely populated. And when some of the UN workers came and the UN peacekeepers came to help distribute stuff, they made a poor decision and put their latrines and their bathrooms right near a creek that ran off. And so some of their like pit toilets, all of their waste was leaking into a creek, which then spread and turned into a cholera outbreak into the rivers. And people were using the rivers to drink water because there was no other water source on the island. And so that spread a huge cholera outbreak, and over 200,000 people died from this earthquake. That's how bad this one was. And surprisingly, that's not the most deadly earthquake in Earth history here, but just tragic and terrible. So how can we figure out ways to make sure this tragedy doesn't happen? That's one of the big things we're going to be talking about. But first, we're going to go back into your groups again really quick. And I want you to come up with 3 comparisons here. There's a comparison of a map of the magnitude 6.9 Loma Prieta earthquake in 1989. There's the magnitude 7, which is, if you do the calculator here, right, it's, hardly any difference at all. Oops, let me go back here. We do the calculator to magnitude 7 and a 6.9, and we do calculate, right? I mean, it's 1.25 times bigger, 1.4 times the amount of energy. So almost identical, all right, almost identical. So my question then is, oops, where do we go? Here it is. Make sure I can edit it, and then I'll tell you what the question is. All right, chats, boom, boom, there we go. My question here in this next breakout bit, and we'll do this for about 6 or 7 minutes. You don't have to research or do a lot of other things. But I just want you to compare the magnitudes of each of these earthquakes, which we just did. And then I want you to create 3 hypotheses as to why do you think the intensity and the damage was so much greater in Haiti compared to Loma Prieta here in California, right? So the magnitudes were identical. So what do you think? What could be 3 reasons that you can come up with just in your own ideas of why one was so much worse than the other, or why it wasn't so bad here, or why it was so bad over there? And if you want links, you can click on these links if you wanted to and see like all the damage pages, but you don't need to for that. So I'm gonna put you in your breakout groups for about 5 more minutes, six minutes, somewhere in that neighborhood. And I just want you to try to come up with 3 ideas, 3 hypotheses of why one was so much worse than the other. What do you think could maybe cause that? So all ideas go. I don't want you to Google it or anything like that. This is just kind of your own idea in your own groups, trying to figure out and talk through it. Okay. Let me go to breakout rooms. And yeah, we'll do this one for about 7 minutes here. That'll give you more than about 2 minutes here of each one to pop. And if you guys finish early, I'll close them early. So here we go.
You're muted.
Thank you. There we go. That's good. So what I was trying to say is that I ended it just a little early because everybody was rolling pretty good on this. But some of the different things that folks were talking about that kind of were common were weak structures or poor foundations. Maybe it was near a fault. I saw some folks said that maybe they didn't have the right resources to build buildings. Maybe is on the fault again. Maybe being on a small island had something to do with it, or that maybe there wasn't as much population was one that came up, which was pretty interesting. So because where the maximum in shaking intensity wasn't underneath all those people, maybe that reduced the amount of death and damage too. And it turns out that, yeah, basically everything that you guys said has a lot of validity to it. And being an island here as well, the further away you get from the epicenter of these things, the shaking actually reduces. And so we'll talk about that for right now before we head off for the afternoon. So great job with that, figuring out kind of what might be some of those controlling factors, I guess. And so here's a better way of presenting it than me just talking. All right. So it's kind of a cool thing to show the difference between magnitude and the difference between intensity.
Magnitude and intensity are both related to the size of an earthquake, but they each measure different aspects. Magnitude, which measures the energy released at the source of the earthquake rupture and is calculated using measurements from seismic instruments, is one single value. Seismic intensity, which is the measurement of the strength of shaking at a specific location, determined from effects on people, human structures, and the natural environment, produces a range of shaking intensities in different locations. Thus, unlike earthquake magnitude, which is the same for all locations, the seismic intensity you feel depends on where you are. Intensity is mostly controlled by three factors: magnitude, how big the earthquake was; distance from the hypocenter, intensity varies from place to place; and the local rock and soil conditions. Let's compare magnitude and intensity by using a light bulb as an analogy. The light bulb represents the location within the earth called the hypocenter, where the earthquake begins. The magnitude or size of an earthquake is like the wattage of a light bulb. Just as the wattage represents the amount of power of the light bulb, the magnitude is related to the total amount of energy released by the earthquake's source. The intensity, or shaking level, is like the amount of light from a light bulb at any spot in a room. A small light bulb in one area of a room will make that area bright with high-intensity light, but it will leave the distant areas of the room dim with low-intensity light. So, a given earthquake has only one magnitude, but will produce different intensities of ground shaking, as shown on the USGS Did You Feel It intensity maps.
So this is also, I just want to mention too, if there is an earthquake that happens in California that you feel it, one of the things you can do is go to the USGS website, and they have a Did You Feel It website, what do you call it, survey for the earthquake. And you can go and tell them if you felt it or didn't feel it. And that's really big news for them, because it helps them quantify just how bad the shaking was in some areas. So just like we mentioned, and just like the video said, the intensity is varied based on the magnitude, the distance away from the epicenter, the depth. So if you had an earthquake that happens 200 miles down versus, just a few miles beneath the surface, that's 180 less miles that the energy has to travel and dissipate through before it gets to the surface. So usually deep earthquakes are not nearly as destructive as shallower earthquakes, right? The soil and rock type, and we're going to figure out what types are more damaging and which ones are more safe. And then the building designs, and then the population. And for those building designs, the ones that flex or can slide with some waves, that's what we're looking for. That's the good stuff. Buildings that can't flex, that's bad because they'll just shear and break. And here's the Did You Feel It pages. If you do feel it, you go to their website and you click on it, and then it'll calculate for you what the intensity was that you experienced. So I haven't experienced anything massively big or huge, anytime recently here. And so here's a little bit more, one last one about the intensity, and then we'll call it quits.
Now let's examine how intensity of ground shaking is controlled by distance from the earthquake. This shake map for a magnitude 7.0 earthquake in Mozambique nicely illustrates a bullseye map pattern, with intensity decreasing with distance along the surface away from the epicenter, just like the light from a lamp is less bright the farther away we are from the lamp. By analogy, we expect shaking to decrease as distance increases away from the earthquake. Remember, earthquakes occur inside the Earth, not on Earth's surface, so let's consider the effect of earthquake depth on ground shaking intensity. To see this principle applied to earthquakes, let's examine two earthquakes of the same magnitude with nearby epicenters, but with hypocenters at different depths. In 2015, the magnitude 7.5 Hindu Kush earthquake occurred 212 kilometers below Afghanistan. Although strong shaking was distributed over a broad area, only 399 lives were lost. The hypocenter of the 2005 magnitude 7.5 Kashmir earthquake was only 23 kilometers deep. Severe ground shaking was concentrated near the epicenter, causing extensive damage to buildings, with over 87,000 fatalities. In 1989, the magnitude 6.9 Loma Prieta earthquake occurred on the San Andreas Fault System near Santa Cruz, California. Ground shaking intensity and resulting damage was strongly influenced by local rock and soil conditions. In fact, the most severe damage occurred in Oakland and San Francisco's Marina District, 100 kilometers from the epicenter, where violent intensity 9 shaking was greater than that experienced by many areas closer to the epicenter. Both are built on mud substrate. A dramatic and tragic example of shaking amplification is the double-decker Nimitz Freeway constructed on bay mud. 4 seconds after drivers felt the earthquake, the Nimitz Freeway shook and swayed and sections collapsed, taking 42 lives. Seismograms from nearby stations document.
So we're going to take a little bit more look at this tomorrow or Thursday. But yeah, the Nimitz Freeway collapse was terrible, and we're going to see that mud and sand and things like that, loosely compacted sediments, not good to build stuff on, and we'll figure out some of those hazards. So that's where we're gonna end it for today, and then we'll come back and pick up the different hazards and how we protect ourselves from it. And one life lost is too many, and so if we can do anything we can to prevent that, I think that's something we should try to do. And that's hopefully what we'll have the arsenal to deal with by the end of Thursday here, how to know and keep ourselves safer. All right, so good job with that. Now know magnitude versus intensity, piece of cake. And I'll see you on Thursday for the exciting conclusion of all the things that earthquakes can do and how we can stay safe from them. All righty, so that's what I got for today, and I'll see you Thursday.
Bye. Have a good day.
Thanks. See you later.